Hi everybody. This is our lecture on sections 2.1 and 2.2. So we'll do a combined lecture on these sections. Most of the other sections we'll do one at a time. So this is on vectors and coordinates. In 2 dimensions and 3 dimensions. Okay, so recall the 2-dimensional plane and its coordinate system. Its XY coordinate system, we'll say. So we had 2 axes. There was an x-axis and a y-axis. Right, and then, each axis is a number line for the real numbers. So if you picked a pair of numbers, 1, 3, something like that, you use 1 on the x-axis, 3 on the y-axis, and you get this point 1, 3. Probably I made that a little too much to the right. There we go. Or, another point here, 2, 1. Right, that's 2 on the x-axis, 1 on the y-axis, and you get this point in 2-dimensional space. And of course, you also have these negative points as well. So -1, 2, so on and so forth. Okay, so that is the coordinate system in the 2-dimensional plane that you've been accustomed to for many years now. And this generalizes readily to 3 dimensions with 3 coordinate axes. So in 3 dimensions we have 3 axes. So we think of this as the x-axis, this is the y-axis, and this as the z-axis. And you kind of have to imagine that the y-axis and the z-axis are on the page, and they're perpendicular to each other, just like the y and the x here. But this is y and z. And then the x comes straight outward from the page, so that the x is perpendicular to the y-axis, and the x is perpendicular to the z-axis. And of course, these are perpendicular to each other. So you can put the corner of a cube right here, right? And it'll touch all 3 axes. Okay, so it's a projection of a 3-dimensional image. And if you pick a point on the x-axis, okay, we'll call that A, and a point on the y-axis, we'll call that B, and a point on the z-axis, C. Right, and we form this box like so. And I will explain more about these lines in just a minute. Okay, then this point right here is the point A, B, C, right here. So here we are. Okay, that's the point A, comma B, comma C. So down here is the point 0, 0, 0. This is the point A, 0, 0. X coordinate comes first. 0, B, 0. A, B, 0. A, 0, C. 0, B, C. And then again, this is the point A, B, C. Okay. Now, what's special about these lines? Okay, each line on the box is parallel to one of the coordinate axes. So the vertical lines are parallel to the z-axis. The lines that go in this left-right direction, those are parallel to the y-axis. And these other lines that are coming out are parallel to the x-axis. And you'll notice that mine are not quite right. These points should be slightly lower so that we get the right slant. There we go. And now these points are more where we want them. All right, so each line here is parallel to one of the coordinate axes. These four are parallel to the x, these four up and down parallel to the z, and these four left to right are parallel to the y. Okay, so that's kind of the first sort of idea in how to draw these three-dimensional shapes that are more or less rectangular. All right. Now, so those are the coordinate systems. Now, some special lines and planes, lines in 2 dimensions and planes in 3 dimensions are as follows. So in the 2-dimensional plane, right, where you have the x and the y axes, if I said to you that y equals 5, then that's this line right here. Right? If this is a 5 on the y-axis, then the line y equals 5 is all points xy, where the y-coordinate is 5 and the x-coordinate is whatever. Or if I said x equal to 7, like right here, if that's 7 on the x-axis, then this is the line x equal to 7. Right? Every point on this line has x equal to 7 and the y-coordinate is arbitrary. Right? And where these two intersect is, of course, the point 7, 5. So those are lines that are parallel to, so the line x equal to 7 is parallel to the y-axis, the line y equals 5 is parallel to the x-axis. So we know about those. In 3D, so we have our x, y, and z axes. If we take these coordinates here, these points that where x is equal to 0, so y and z are arbitrary and x is equal to 0. That's the collection of these points here. And that's known as the YZ coordinate plane. or just the YZ plane. Each point has x equal to 0. Right? Well, so that's the plane where x is equal to 0. But, I mean, I could... Let me fix that up a little bit. There we go. I could say maybe let's look at the points where x is equal to 3 or something like that. So if I said x was equal to 3, and let's do this one in blue. So x is equal to 3, and then y and z are equal to any other coordinate, then I have a plane that is parallel to the YZ plane. So this is the point, the plane x equal to 3. So x is equal to 3, and y and z are anything. And this plane is parallel to the YZ plane. Right, so the plane x equal to 3 is parallel to the YZ plane. So whereas when you say x equal to 3 in 2 dimensions, you get a vertical line. When you say x equal to 3 in 3 dimensions, you get a plane parallel to this YZ plane. And you can do that with the other coordinates as well. So x, y, z. If I just look at the points on the floor here, notice, by the way, how I'm drawing these planes. I'm using lines that are parallel to the coordinate axes. Here, they're parallel to the y and the x-axis. So this is the xy plane, right? And all points have z equal to 0. And then if I said, say, z equal to 4, well, that's going to give me a plane where the z coordinates are all 4, and we're parallel to the xy plane. Alright, so this is the plane z equal to 4. If this is the point 4 right here, it is parallel to the xy plane. Alright, and then of course we can do the other pair of coordinates. So let me make these move over just a little bit. Let's see. I guess I gotta do it on the next page. Alright, x, y, z. This plane over here is the xz plane. All points have y equal to 0, and then if I said, say, like y is equal to 2, alright, so if this is 2 on the y-axis, And this plane here, let me maybe move it over, y equal to 4, say, is going to be this plane that's going to be parallel to the xz plane. So this is 4 on the y-axis, this is y equals 4, parallel to the xz plane. Let's see, like that, and then like that. There we go. Okay, so those are the analogs of the analogous objects to the vertical and horizontal lines in 2 dimensions. So this one is not really parallel to that in the way that I've drawn it. Let's see if we can't fix it a little bit. There we go. I think that's a little better. Yeah. Okay. So those are the 3 what are called coordinate planes, and then planes parallel to those coordinate planes. Okay. Vectors. Given 2 points, P and Q, in 2D or 3D, the vector, so let's go PQ like this, and that's got a little arrow on the top of it, or a little sort of harpoon on the top of it, is the directed line segment, well, the line segment directed from and head Q. So the tail and the head. So here you've got P and here you've got Q. So the vector PQ is this line segment here. Okay, we represent the vector with coordinates obtained from Q and P the coordinates of Q minus the coordinates of P. So, for example, if you've got the point in 2 dimensions, say, so if this is the point 1, minus 1, and this is the point 2, 4, right, this is P, and this is Q, then the vector PQ is equal to, and then instead of using round parentheses, we use these sharp brackets here, head minus tail. So coordinates of Q minus the coordinates of P, head minus tail. 2 minus 1 is 1, and then 4 minus 1 is 5. Okay, notice that this same vector, 1, 5, can also appear between, several other points, right? If we had 0, 0, so this is point A, say, and if this was point 1, 5, then here, point B, then the vector AB is also equal to 1, 5, head minus tail, 1 minus 0, 5 minus 0. So the same vector, can appear between 2 distinct points, and what you'll notice about those 2 vectors is that they are parallel. So I should make them look parallel by copying and pasting. Alright, so if this was point A, B, then the vector AB is the same as the vector PQ, right, which is equal to PQ. Same vector, even though it appears between two different points. You know, as a matter of fact, for any point that you pick, you can still get that same vector there by just adding it to the tail, right? I mean, I could also do, say, pick anything here. 3, -2. And then this is the vector 1, 5. So if that's the vector 1, 5, then what does the head need to be? Well, I'm just going to add the vector to the head, right? So head minus tail is equal to the vector. Or sorry, I'm going to add the vector to the tail. So tail plus vector is equal to the head. So 3 plus 1 is 4, and then minus 2 plus 5 is 3. So 4, 3, minus 3, 2 is again 3 minus 2 is again the vector 1, 5. Similarly, in 3 dimensions, if I had points 1, 0, 1, and 0, 5, -3, like this, right, then here we have the vector. And the way you normally denote a vector is as letter V or letter U, and then you put a little sort of head on the top, or a little harpoon on the top for a vector. Now, in the book, they'll use a bold-faced V, but it's not really easy to do when I'm writing by hand, so we just use these arrowheads. So 0 minus 1 is minus 1, 5 minus 0 is 5, minus 3 minus 1 is minus 4. Right, so these vectors are all vectors in 2 dimensions, whereas this vector I just drew is a vector in 3 dimensions. Let's see, maybe we can put these all on the same line. No, not gonna fit. All right, or I could also have, notice by the way, oops, let's do something different. What if I just flipped around the head and tail? All right, I'll make this the head instead of the tail, and this the tail instead of the head. Well, then what do you get here? What vector do you get? Well, if you're reversing head and tail, then all it does is negate the coordinates of v. So this becomes what's known as the vector negative v, which is 1 minus 0, positive 1, 0 minus 5, negative 5, and then 1 minus minus 3 is positive 4. So whereas this is negative 1, 5, negative 4, this is 1, negative 5, positive 4. Right? And that's known as the vector minus v. Okay. Adding vectors. So, given 2 vectors, u with an arrow and v with an arrow, the vector, well, these vectors, they can be used to describe the sides of a parallelogram. Right? The sum u plus v is the vector shown, which is one of the diagonals of the parallelogram. Right, so if I had, say, u like this and v like that, drawn tail to tail, right, so I have the vectors drawn tail to tail, well, of course, I have a copy of u over here at the head of v. Come on. Right, so that's vector u. This is also vector u over here. It's the same line segment, it's just between two different points. And also I have another copy of v right over here, parallel to the other copy of v. Right, so here I have the vectors u and v drawn tail to tail. Here I have v and u drawn tip to tail, or head to tail. And here I have u and v drawn head to tail. And then the sum u plus v is just this vector here. Right, so the tail of u plus v is the common tail of u and v. And the head of u and v, u plus v, is the common head of u and v. So you have this parallelogram made by the vectors u and v, two copies of u, two copies of v, drawn tail to tail and head to tail. And then the sum is just these two right here. Right? So this is v, u, u plus v, u, v, and u plus v. Now, what is the other diagonal? Is u minus v and or v minus u, depending on which direction you take. Right, so right, here's this parallelogram again. Now, this vector here right, this is v plus x equals u. Well, v plus x equal to u, this must be u minus v. Right? V plus u minus v is just equal to u, right? Because this vector here is drawn head to tail with v. So this plus this must equal this. Right? This plus this, by definition, is this, the completion of that triangle, the third side. One side of the triangle, two sides of the triangle, third side is the sum. Well, here we're doing the same thing. One side of the triangle, two sides of the triangle, their sum must be u. So this side must be u minus v. So that's if you draw it in that direction. If you draw it in the other direction, it's v minus u. You flip it around. Right, u plus this equals v. So u plus v minus u is just v. Alright, so depending on which direction, it's either u minus v or v minus u. So that's a neat property of that parallelogram. Arithmetically, vector addition is just the sum of the coordinates of the vectors. of u plus v are the sums of the coordinates of u and v. All right, so for example, all right, if I've got the vector 3 minus 1 plus the vector 2, 2, right, this is equal to 3 plus 2 is 5, minus 1 plus 2 is 1. Or if I had 3 dimensions, 3, negative 1, 0, plus 1, 0, 1, this is equal to 3 plus 1 is 4, minus 1 plus 0 is minus 1, 0 plus 1 is 1. All right, and why is that the case? Well, if you just look at this picture here in 2 dimensions, right, if this is vector a plus b, right, so this is the vector a comma, sorry, not a plus b, vector a comma b, right, then this length right here is a, and this length right here is b. Right, it just has the vector whose x-coordinate is a, whose y-coordinate is b, whose tail is the origin. Tail is the origin, head is a plus b. And then if I had another vector here, say c comma d, well, same thing. This here is c, this here is d, this length here is c, this length here is d. Right, now this length here is a plus c. This length right here is b plus d. Right, but this vector here is the sum, ab plus cd. So AB, CD, and this is the sum AB plus, let's do that one in red, AB plus CD is equal to A plus C, B plus D, and we see that right there. All right, this is one side of the triangle. This is the other side of the triangle, where the coordinates are broken down into x and y coordinates, components. Right, and then you just put them together like this, and then the x component of the third side is the sum of the x components of the first two. Right, and the y component of the third side is just the sum of the y components of the original two. Right, so we define the sum geometrically, and we get that it has a simple arithmetic form as well. You could define it arithmetically and then show that the geometric form looks like this. They're equivalent to each other. Okay. So that's vector addition. You can add vectors. Another thing you can do is scalar multiplication. Or sorry, let's talk about the length of a vector. Of v equal to a b is, so you denote it like this, v with these absolute value symbols around it, and you just call it length, right, is equal to the square root of a squared plus b squared. And that comes from the following, right, if this is the vector v equal to the vector having coordinates a and b, well, that makes this vector the hypotenuse of a right triangle, again, like we were talking about before, with one leg of length a, the other leg of length b. And therefore, this leg, the hypotenuse, has length a squared plus b squared. Square root of a squared plus b squared. All right, so that a squared plus b squared is equal to c squared. And then in 3 dimensions, so that's just the square root of a squared. So it's got this form here. It's the square root of a squared plus b squared plus c squared. It's sort of a 3-dimensional analog of the Pythagorean theorem. And it looks like this. So if I make this box here, hopefully we got that right. Yeah. So we've got this box here like this, where these sides have length b, these sides have length a, b, 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 and these up and down sides have length c. Okay, so now if we've got this vector, let's do it in a nice bright color. From here to here, that's the vector A, B, C. This green vector is the vector A, B, C. If you project that vector down here, and we'll make it, say, red down over here, from here to here, this is just the vector AB, 0. And we know the length of AB, 0, is square root of a squared plus b squared. So let's zoom in. There we go. So that's the vector ABC. This is the vector AB0. And then this length right here in orange is just C. Alright, so this length is square root a squared plus b squared. This length right here is C, and of course these lines are perpendicular to each other. So the length of this side is the square of this plus the square of that. So c squared plus a squared plus b squared, square root. So the length of this side here is, I'm going to get rid of that. Get rid of that. A squared plus b squared plus c squared. I'm going to get rid of this. Alright, so it's a 3-dimensional analog of the Pythagorean theorem. Alright, so that's the length of a vector in 2 dimensions. That's the length of a vector in 3 dimensions. Okay. So now, let's look at this operation called scalar multiplication. Given a vector v, equal to A comma B, or V equal to A comma B comma C, and a real number, K, define K times V as follows. So we're not multiplying two vectors together yet. We'll do that later. We're taking a vector and a real number. K times V, when it's AB, is this. It's just KA comma KB. When the vector is in 3 dimensions, it's KA, KB, KC, like that. Geometrically, K times V has length that the length of K times V is the absolute value of K times the length of V. And the direction of KV is the same as V when K is bigger than 0, and the direction of KV is opposite to V when K is less than 0. So it looks like this. So, make it a little shorter. If this is the vector V right here, if this is a vector V right here, then two V is going to be a vector of twice that length with the same direction. So this is the vector 2V right here. This would be the vector 1/2 of V. So we scale the length of V by a half. It doesn't have to get longer, it can get shorter. 1/2 of V. If we make it negative, then it just points in the opposite direction. Like that. But the length is the same. The length is the same, but the direction is opposite. So 1/2 of V, negative 1/2 of V, 2V, and then just minus V itself is the same as vector V, just flipped 180 degrees. Okay? A vector, so for example, we'll say V is, how about this? 1, 2, negative 1, 3V minus 3V is therefore equal to minus 3 minus 6, positive 3. The length of V is equal to the square root of 1 plus 4 plus 1, just square root 6. And the length of minus 3V is equal to 9 plus 36 plus 9, which is the square root of, so 36 plus 18, 54. But 54 is 9 times 6. Right? That's 9 times 6. So that's 3 square root 6, which is 3 times the length of v. Right? So the length of v is square root 6. The length of negative 3v is 3 times the length of v. Right? The length, of course, is always going to be positive. Another example, notice that the length of v is always bigger than or equal to 0, with the length of v equal to 0 if and only if v is what's known as the zero vector. So the vector whose coordinates are all 0. What time again? 46, that's fine. The vector whose coordinates are all 0, like that. Okay. So we've got several operations with vectors now. We've got this scalar multiplication, we've got this addition, and then we know this thing about length as well. Here are some basic algebraic properties. One u plus v is equal to v plus u, right? Because when you're just adding coordinates, regular addition of coordinates of real numbers is commutative, so therefore vector addition, which is just adding up coordinates one by one, has to be commutative as well. The scalar 0 times v is the zero vector. So v is equal to what's known as the zero vector. So the zero vector in 2 dimensions is the vector 0, 0. In 3 dimensions, the zero vector is 0, 0, 0. So scalar 0 times v is equal to vector 0. 3 u plus v plus w, if you want to add up 3 vectors, v plus w first and then add u to it, it's the same as adding u and v. All right, that's called associativity, commutativity, associativity. You also have distributivity, the scalar product of k times the sum of u and v is just the scalar multiple kv, or ku, plus kv. We also have distribution like this. K plus L times V is equal to K times V plus L times V. And 6, we have associativity like this. K times L times V is K times L times V. So some basic properties for vector addition and scalar multiplication, and of course you have to show that they're true, but it's all pretty straightforward, so we'll just take those as known. All right. Definition. So a vector u is called a unit vector when the length of u is 1. Right? So, for example, the vector I hat is equal to 1, 0 in 2 dimensions, and the vector j hat is equal to the vector 0, 1, are both unit vectors. In 3D, I hat is 1, 0, 0, and j hat is 0, 1, 0, and k hat is 0, 0, 1. Are unit vectors in 3D. Both unit vectors in 2D, we'll say. Are all unit vectors in 3D. So the picture would look like this. Right, in 2 dimensions, I and j would be right here. This would be I. This would be j. And in 3 dimensions, I, j, and k would look like this. Right, I have coordinate axes, x, y, and z. And here, I is right here. J is right here. And k is right here. Okay, so those are unit vectors. They're sort of standard or elementary unit vectors, if you will. But of course, not every unit vector looks like that. If I had vector v equal to 3, negative 4. So the length of v is equal to square root of 9 plus 16, which is equal to 5. All right, given v equal to this, the length of v is 5. So therefore, 1 over the length of v times v, which is equal to, in this case, 1/5 of v, which is equal to 3/5 minus 4/5, is a unit vector. Right? This vector v has length 5. So if I multiply it by 1/5, right, then its length is 1. Right? Given a vector in 3D, v equal to 3 minus 3, 1, like that, 3 minus 3, 1, the vector 1 over the length of v times v. And what's the length of v? Square root 19. So this is equal to 3 over square root 19 minus 3 over square root 19, 1 over square root 19, is a unit vector in the same direction as v, and minus 1 over the length of v times v, I'm just negating it, is minus 3 over square root 19, positive 3 over square root 19, negative 1 over square root 19, is a unit vector in the opposite direction as v. Okay? All right. So that's some basics about vectors and coordinates in 2 and 3 dimensions. Some special objects in 3 dimensions that we'll definitely need to know about throughout the semester are as follows. Spheres, circles and spheres. All right, in 2 dimensions, if I had a circle centered at the point HK of radius r, what is that exactly? It's the set of all points at a distance r from HK. So that's all points whose x coordinates and y coordinates, when squared, the difference of the x coordinates, the difference of x and h squared plus the difference of y and k squared must be equal to the radius squared, right? We've seen this before. In 3 dimensions, if you took a similar sort of thing, instead of a circle, we want a sphere. So you have some center point. What's that center point going to be? We'll say HKL, and the radius, again, is little r. Then that's all points x, y, z, whose distance from HK and L is r. So it's all points that look like this: x minus h squared plus y minus k squared plus z minus L squared square root equals r. But normally we don't write it with this square root, we just square the r instead. Right, so we have circles in 2 dimensions and spheres in 3 dimensions. Right, that have similar sorts of equations. So, for example, the equation x squared plus y squared plus z squared minus 6x plus 8y minus 10z plus 25 equals 0 represents a sphere in 3D. Find its center and radius. Right, so that's the equation of a sphere, although it's been multiplied out and like terms have been collected. So what we want to do is reverse the process and factor it into x minus h squared, y minus k squared, z minus l squared equals r squared. So in order to do that, we're going to have to complete the square. So we take this equation here, alright, I'm going to put the x terms together, x squared minus 6x plus y squared plus 8y plus z squared minus 10z equals minus 25. Put the constant term on the other side. And complete the square for x, y, and z. We take the coefficient of x, coefficient of y, coefficient of z, divide by 2 and square it. So 6 over 2 is 3, squared is 9. So I get x squared minus 6x plus 9 over here. And then I have to add the 9 over here. Plus y squared plus 8y. 8 over 2 is 4. Squared is 16. So I add 16 on the left and I add 16 on the right to keep the equation balanced. And then over here, z squared minus 10z, 10 over 2 is 5, squared is 25, so we add the 25 over here. So this becomes x minus 3 squared plus y plus 4 squared plus z minus 5 squared equals positive 25. All right, so the center is 3, negative 4, 5, right? Positive 3, negative 4, positive 5, right? Because it's x minus h, y minus k, z minus l. So the coordinates are the negative numbers there. Right? So here the center is 3, negative 4, 5. Center is that, and radius is the square root of that, which is 5. Okay? So that's spheres in 3 dimensions. So spheres are, important objects in 3D, and we'll talk about them quite a bit. Some other objects which come up quite a bit are cylinders. So cylinders occur with equations using just 2 of the variables. All right, so it's not a cylinder in the usual sense. It's a cylinder in the sort of looser sense. Equations using 2 and 3 variables produce cylindrical, in quotes, surfaces. So, for example, x squared plus y squared equal to 1. Well, in 2 dimensions, x squared plus y squared equal to 1 is the circle of radius 1 centered at the origin. Right? So x and y give you this circle of radius 1. Okay, but what about the z? Well, it says nothing about the z, right? There we go. Come on. What's going on here? Oh, here it is. Okay. So it says nothing about the z. So the z can be anything. X and y are what are constrained. X and y are what are constrained, but the z is unconstrained. Since the z is unconstrained, it can be anything. So the x and y form that circle, and then you extend that circle parallel to the z-axis. Oh, that's not a good picture. All right, so x and y are constrained to make that circle, and then you extend that circle in the z direction, parallel to the z-axis. And then you have various copies of that circle at all the different z coordinates. Like that. All right, so in 2D, you just get that circle of radius 1. So that's x, that's y, and then in 3D, you still have that circle of radius 1, but then you extend it in the z direction. So that's an example. And that's an actual cylinder. Let's try something different. Let's say z is equal to x squared. Well, if z is equal to x squared, then in the xz plane, you get what? You get this sort of standard old parabola, yeah? So what do you get in 3D? Well, in the xz plane, you get that parabola, and it's skewed a little bit this way. So you're looking at it sideways. Still no good. There we go. All right, so in 3D, what you get oops, I should have did this. Is you get several copies of that parabola, well, infinitely many copies of that parabola extended in the y direction. So you get this sort of parabolic cylinder, as it's called. Maybe we can move that out. All right, so this is x, y, z. So z equals x squared gives you this parabola in the xz plane, and then you just extend it in the y direction, in the missing variable. And that's called a cylinder as well. Right? It's not a cylinder in the sense that it's a round circular cylinder or this tin can kind of thing, right? But in the sense that you have an object in one plane, and then you extend it in the third direction. Right? So you have this object in one plane, coordinate plane, then you extend it in the third direction. Right? So that would be called a parabolic cylinder. All right, and you can do that for any, sort of common graphs that you get for two variables in two dimensions. Okay, so this is kind of a long lecture. This one, the rest of them will be a little bit shorter than this, but anyway, this is the end of the lecture on this section.